Well, yeah, let me look it up in my book here and get to that section, because I don't usually memorize those.
Okay.
Let's see. Yeah, I think this book has all of them.
I can probably also look it up real quick.
I've got them here.
Oh, okay.
Here. I'm not sure whether this is all that helpful, but here, let me give you some formulas that are in my book. If you have the form R equals 2a times sine of theta, that is a circle with radius a.
Okay.
And its center is at 0, comma a.
Okay.
Okay. And then you have other similar kinds. That's also a circle. It's also a circle. Now this one uses cosine. The radius is still equal to a, but the center is probably, my guess, going to be a comma 0. Yep.
Mm-hmm.
Now, and there's a fourth one there for circles. In other words, these are going to be, here, let me just show you what the difference of each of these are. The first one centered up here, and it looks like that, because its radius is a.
Mm-hmm.
The second one centered down there with radius a. The third one centered right there with radius a, and obviously the fourth one is right there. So if you wanted the equation of any of those four circles, it's one of these four over here.
Okay.
Okay. I don't know that that's so helpful. I don't have any of those memorized, and I can give you, here, let me just give you the cardioid formulas. If you have R equal to some A, which is just a constant, there's four of these also. And as you can imagine, one of them is going to look like this, and rotate that 90 degrees to get your other three.
Mm-hmm.
And the other three have this kind of form. So whenever you see a polar equation that is of this format, you know it's a cardioid.
Okay.
Okay? Just like the polar equation for a circle. Now, you might ask, well, one of the advantages I said about polar equations is the equation of a circle is really simple. Okay, R equals 3 is a circle, but its always a circle whose origin is the center.
Right.
So these more complicated equations, those are of cardioids, but even the 4 that I gave you for circles were equations of circles whose center is not at the origin.
Okay.
Now, you've got all kinds of different shapes. Another one is a Limacon. And it has its own equations. I'm not expecting you to memorize these, but it does give you a little bit of an idea as to what the equation looks like. This is one equation for a Limacon. And a Limacon is like a cardioid. Oh no, a Limacon has a loop. So a Limacon looks like this. So it's like a cardioid, only a cardioid doesn't cross back over itself,
Mm-hmm.
whereas a Limacon does. And this is the general format for a Limacon. The loop has an inner loop. Only difference between a Limacon and a cardioid is the Limacon has an inner loop. Rose petals. Let's talk about those. Their equation is fairly simple. And that specific one is a rose petal with 4 petals, precisely. And it makes a loop there, a loop there, a loop here, a loop there. And I believe you get the 4 petals from the 2 times 2. In other words, if that was 3 cosine of 2 theta, I think you'd have 6 petals. Did we go through how you actually graph these?
Yes, I think we did a couple.
Using a table? In other words, if I were to do, let's just do this one, just so you can kind of see how you get that rose curve. I won't do a lot of points, but we can certainly get started.
Okay.
That's the way all the tables look. Now, when theta is 0, r is 2, and theta is pi over 6, r is 1. When theta is pi over 4, r is 0. When theta is pi over 3, r is negative 1. And finally, when theta is pi over 2. Notice I go from 0 to pi over 2.
Mm-hmm.
Well, what that tells me is r, when theta is 0, r is 2. So that point is on the curve, right there. With me?
Okay. Yeah.
When theta is pi over 6, 30 degrees, r is 1.
Mm-hmm.
So it's about there. When theta is pi over 4, 45 degrees, it's right there. So if I was graphing this from 0 to pi over 4, I would get that part of it.
Mm-hmm.
And now, if I want where pi over 3 is, r is -1, which is about there. You see how I get that? In other words, pi over 3 is 60 degrees, which is this angle, but it's a -r, so you got to go in the opposite direction. So that's how I get this point right there.
Okay.
And then when theta is pi over 2, r is -2. So you can kind of see when I rotate theta from 0 to pi over 2, I get that part of my rose curve. Now,
Okay.
if I go from pi over 2 to pi, let's go like this. And then when I go from pi to 3 pi over 2, I get that loop. Then when I go from 3 pi over 2 to 2 pi, I get that petal. So that's how you get a rose curve out of that. And
Okay.
the format for rose curves are r equals a cosine of n theta and r equals a sine of n theta. And n, hold on, if n is even, the rose has 2 times n petals. In other words, n was even there, so we got 4 petals, not because of this 2 in front. It's just,
Okay.
if it's even, you have 4 petals. If n is odd, it has n petals. So if I made this 3 theta instead of 2 theta, I've got a rose curve that's going to look something like this. All of it goes through the origin. I meant to bring that down like that. So it's actually a lot easier to deal with rose curves because you can figure out immediately what they're supposed to look like. Almost immediately. Certainly you know how many petals it has based on n.
Mm-hmm.
Here's kind of an interesting one. Let's look at this one. I'm not quite sure how you do these. If you have this function, if you make a table and connect the dots, you get, first point is right there. In other words, when theta equals 0, the sine of 0 is always 0, so r would be 0. So you see why when theta is 0, our point is at the origin. R has a length of 0.
Okay.
Okay? When theta is pi over 6, r has a length of plus or minus 1.9. Hold on a minute. Yeah, okay. So an R at 30 degrees the plus side would be that. In other words, that would be 1.9 comma pi over 6. That's where that point falls. And then as you go from 0 to pi over 2, I think you get two ends of this thing. Yeah, hold on a second. Let's see, as you go from 0 to pi over 2, this curve ends up looking like this. Now, the question is, why do we only have two petals when n is 2, which is even? Now, when n is even, you're supposed to have 2n number of petals. So it seems to me we should have two more like that. Looks to me like you get, if you, yeah, according to this, you get one petal for every 90 degrees. In other words, when they go from 0 to pi over 2, they get this petal right here in the drawing.
Okay.
Now, this doesn't address what to make of that plus or minus. Hold on a minute. Let me just quickly read this. Note that there are no points on the graph when theta goes from pi over 2 to pi. Why not? What is R when theta... I see why. I see why. Notice that the moment you get to pi over 2, or when theta is greater than pi over 2, 2 theta is in the third or the fourth quadrant, right?
Okay.
So the sine of a third or a fourth quadrant angle is always negative. So when theta is between pi over 2 and pi, that's negative, always. And yet r squared is equal to that, which is impossible. So that's why there are no r values when theta is between pi over 2 and pi. Now, once you get from pi and go from pi to 3 pi over 2, you pick up, you know what, it's showing this as a final answer. 2 loops only, which I'm not sure I understand why. In other words, that's what it's actually showing for this equation, is a 2-looped petal. And that's because we're taking the square root of it. In other words, we're not in this form up here. So we can't assume this is n. That is not n. In other words, normally if you had the sine of 2 theta, you would have 4 petals. If you had r equals some number times the sine of 2 theta, you would have 4 petals. But here we have r squared equals that. So r really equals square root of 4, 2 times the square root of sine of 2 theta.
Mm-hmm.
And you still can't call that n is not 2. So sometimes the only way to really plot these things is with a table. In other words, I would have never figured out, unless I was reading in this book, that there are no points on this graph when theta goes from pi over 2 to pi. In other words, we went, on this table over here, we went from 0 to pi over 2, just first quadrant only. Well, as theta goes from pi over 2 to pi, r doesn't exist.
Okay.
So you don't start picking up more points until you get from pi to 3 pi over 2, and that's when you get the second loop. So it goes something like this. And then you get nothing for the next 90 degrees, and the next 90 degrees you get that, and you get nothing for when it's 3 pi over 2 to 2 pi. So you end up with that as your solution.
Okay.
And that's what it means basically is if you make a table, usually these things get traced out once when you go from 0 to 2 pi. Some of these polar curves actually get traced out twice. And to trace them out once, you only need to go from 0 to pi. And that becomes a lot more important when you get into calculus and you're trying to figure out the arc length of this curve. Okay? But one thing I just learned today is that, yeah, if r has no value, it's not at the origin, it's not on there. There is no point for that. And if I made theta 100 degrees, you wouldn't be able to solve this. There's no r squared that's equal to 4 times the sine of 2 times 100 degrees.
Okay.
Because the sine of 200 degrees is a negative number. And r squared is always a positive number. So there's no solution. Or you could look at it as taking the square root of that to give you r, but you can't take the square root of a negative number either. And the sine of 200 degrees is a negative number. So if r doesn't appear in part of the rotation of theta from 0 to 2 pi, it just isn't on there.
Okay.
Now, let me have a second here. The 4-petal rose curve that I had on there previously is traced out exactly once as you go from 0 to 2 pi. And that's important to know, is where you have to, oh, I see, Limacons. Limacons are different than Limacons. They have this formula. So that is a Limacon. And looks like that previous 2-petaled curve. Okay?
Okay.
Now, the last one that they have in my book that's of interest is called Archimedes Spiral. Oddly enough, they don't call it that in my book, but I know that's what it is. They call it a logarithmic spiral. And the general equation for that is e to the theta over 5. Odd, huh?
Huh.
Well,
Yeah.
when theta is 0, what is r?
0.
No, when theta is 0, you've got e to the 0, so r would be 1.
Yeah.
So that point is right there. And if you run it from 0 to 2 pi, you get a Archimedes circle, which looks something like this. It's a spiral. And depending on how many times you go around, depends on how big your spiral gets. In other words, the first loop around got me to there. That was going from 0 to 2 pi. And then the second loop around, I think, gets you to there. The third loop gets you to there, and so forth and so on. So it goes on and on and on. It's also called a logarithmic spiral.
Okay.
And it spirals infinitely both toward the pole and away from it. Okay. Now, the one other thing of interest on these, but I don't know if it's of interest to you, they may or may not introduce you to this concept, and that is symmetry.
Okay.
Fortunately, I'm not sketching a graph of a polar equation quickly by hand. Now let's have a look at this one. I give you this polar equation. If we don't want to go through doing a table and letting theta go from 0 to 2 pi, which is pretty laborious, right? Incidentally, do you know how to draw these, or do you know how to put these into your calculator?
No.
Do you have a TI-84?
Okay.
No, I don't have a TI-84.
What kind of calculator? Do you have a graphic calculator?
Yeah. I have a Casio.
Okay. Does it have a mode for polar as opposed to
Yeah.
rectangular equations? Go ahead and hit the polar and then define your equation as r equals 2 plus 2 sine theta. And it should trace it out, and it will trace it out as it makes theta go from 0 to 2 pi. You'll see it trace it out fully. And you'll end up with a cardioid. That is the equation of a cardioid. And it looks something like this. Now, how do you graph those quickly without tracing it out? Hold on. The period of sine theta is 2 pi. So we form a table and we're going to let theta go from 0 to 2 pi. Compute r for each theta. And so this one says, sketching the graph of a polar equation quickly by hand. And it goes over and it does a table. It goes from 0 to 2 pi. Ah, I see. I see. Okay. Here, I'll go through there. This is worth knowing. Not going to go through every angle, though. It's going to use the principle of symmetry.
Okay.
So it's going to do the first one of 0, which gives you an r of 2. And then the next one is going to be pi over 2, which gives you an r of 4. And the next one is going to be pi, which gives you an r of 2. And then 2 more, 3 pi over 2 and 2 pi. And the 3 pi over 2 gives you an r of 0, and this one gives you an r of 2. So this is quick because it only checked every 90 degrees. You'll notice it goes from 0 to pi over 2 to pi to 3 pi over 2. So if we get those 4 points, we can construct the cardiogram or cardioid.
Okay.
Let me show you how. Hold on. Leave it. All right. If we look at this point right here, we know r is 2. 0. Now, if we look at pi over 2, r is 4. And if we look at pi, r is 2 again. Puts it right there. And then if we look at 3 pi over 2, r is 0, so it's right there. And finally, when we're at 2 pi, r is back to 2. So we only have 4 points there, but we know it's a cardioid because it fits the equation of a cardioid. And it's easy enough to draw. I know what cardioids look like. Basically. In other words, the only thing we really need to draw this cardioid are those 4 points. Those 4 points tell us everything we need to know.
Okay.
So you still need to draw a table. It's just you only need to put 4 points. And in point of fact, if you used symmetry, you would really only need this point, and that point. Because that would give you this part of the cardioid, and you know it's symmetrical with the y-axis. So you would know what the left half of it looked like.
Mm-hmm.
As long as you recognize that that's a cardioid whose, in other words, there's 4 types of cardioids. This could be, if I rotated this 90 degrees to the right, that would be a cardioid, but a different formula. If I rotated it 90 degrees to the left, cardioid, different formula. And if I flip it over the x-axis, it's a cardioid, different formula. But notice the symmetry of all 4 cardioids. They're all symmetrical to either the x-axis or the y-axis.
Okay.
Which makes it easier to draw. You really don't have to do this whole table. Because all I really needed was this point, and this point. All right. Here, let me just tell you one thing that it's mentioning here. In polar coordinates, r equals 1 is the graph of the unit circle, right?
Mm-hmm.
And it does define a function. In other words, for every value of theta, there is only one corresponding value of r.
Okay.
Which is the definition of a function. But notice that it's a circle. So it's a function that does not pass the vertical line test. In other words, this in polar is r equal 1. And it's still a function. We only get one value by the definition of a function. You know, if you're talking about x and y coordinates, if you have a function where you have two different values for y given one value for x, that's not a function. It violates the vertical line test. So I know that in rectangular coordinates, a circle is not a function.
Mm-hmm.
But in polar coordinates, it is. And that comes in really handy in calculus. Sometimes you need things to be functions. So you can treat a circle as a function as long as it's written in polar coordinates. It's not a function if it's written in rectilinear.
Okay. Huh.
Yeah, that's kind of interesting. Since many uses of calculus require that functions be used, the opportunity to express non-functions in rectilinear coordinates as functions in polar coordinates becomes extremely useful. Sometimes something just has to be a function for you to be able to deal with it. So it's not a function in rectilinear, but it is in polar.
Interesting.
Polar coordinates were invented by Jacob Bernoulli in 1691. Amazing. How back then, how they could invent stuff like this. Well, that's the end of my chapter on polar equations and graphs.
Okay.
Were you able to put that into your calculator and have it graph it?
No, I didn't try.
That's worth doing. You should try to do that while we're looking at it here.
Okay. Yeah.
Just because that's the easiest way to sketch a polar equation, right? I mean, you don't want to have to make these tables every time. And you don't want to have to recognize that that's a cardioid. The best thing to do is put that in your calculator and it'll tell you what kind of shape it is. It'll either be a rose petal or a cardioid or a limacate or a limacon or an Archimedes circle or spiral, rather.
So, yeah, let me see.
Try to put that one right there. R equals 2 plus 2 sine of theta. I don't have a Casio, but I'm sure that they have a mode where you're in polar mode, not in XY rectangular mode.
Mm-hmm.
Just have to find it. And then, you know how you would normally put in a function y equals? Well,
yeah.
Once you're in polar mode, you put in a function of r.
Okay. And so it was 2 plus 2 sine of theta?
Yeah. And once you get it in there, now graph it. And it'll graph it in the exact order as you get when you make a table and you go from 0 to 2 pi.
Okay.
You might see it traces twice. I don't think so. According to my book, it looks like this gets traced out once when you go from 0 to 2 pi. So you should only see it trace it out once.
Error. Let me see. I don't know.
You have like a main menu that allows you to choose polar?
Mm-hmm. Yeah, so I have it in the polar, the R equals.
Okay.
It just won't let me graph it because of the window.
Ah.
So.
Ah. You love these calculators. You got to figure out the window before you graph it, and you can
Right.
never see it. You'd think that smart enough that they could at least put the entire graph on there automatically.
Yeah.
Which the Inspire does, I believe. If you have a Texas Inspire, you don't need to define the window. It'll automatically fit it on your screen.
Okay.
I'm not sure what you would want that window, how you would define it so that you can see that cardioid, but I would say that you need to figure out how to do that. Mainly because you might take a test and you might want to see what you're looking at. In other words, maybe the test says, what is that? Well, if you got a calculator, it'll show you a cardioid, and you know what cardioids look like. So,
Range. Yeah.
yeah, so I would definitely advise working with this until you can get it to graph. That's going to be a valuable skill to have.
That's weird. I don't know. I can't figure it out.
Is it something your teacher can show you how to do?
Yeah, she might be able to help me with
Well,
that.
I got another suggestion. Here, let me put it into Wolfram Alpha. We'll see what it does. It's going to I don't have to choose polar. Are you familiar with Wolfram Alpha?
No.
I haven't showed you this before. This is
I don't
better than a
believe so.
calculator, much better. This is called a knowledge database, but it's mainly for math. Okay, so what was it? R equals 2 plus
plus 2 sine of theta.
How do you spell theta? I'll just choose theirs. Notice what happened. The first thing they showed you was the rectilinear graph of it. Right?
Yeah.
Here, let me do it again. I'm going to hit enter. Watch what they show you. First thing they're going to show you is the rectilinear graph, that one curved one. Then they show you the polar graph.
Yeah.
Now, what we didn't see was how it traces it. The advantage of your calculator is the following. In other words, you can get your calculator to do it. You're going to see it starts right there, goes that direction as you start increasing theta. And as theta gets to 2 pi, you end up getting back to there. And being able to see how it traces it is actually helpful. So your calculator actually might be a little better way to do it than Wolfram Alpha. And it still shows us the rectilinear plot. In other words, notice that that is a sinusoid function also. In other words, I put it in as r equals 2 plus 2 sine theta. I didn't tell it that it was polar. So it could have been sinusoid. Sinusoid is this one.
Okay.
Let's see what else it tells us. Tells you it's zeros, it's roots, gives you all kinds of calculus, gives you the period, gives you the derivative. This is is a terrific program to have for anybody that's really into math. Now, I suppose you don't really need to know what is critical to know when you get to calculus, which is, does the figure get traced out once or twice as you go from 0 to 2 pi? A lot of these rose petals get traced out twice. In other words, you really only have to go from 0 to pi to trace them out once. And that's important in calculus because you're going to integrate from 0 to pi instead of from 0 to 2 pi. So it'll definitely make a difference in your answer on all of the important calculus questions regarding polar equations. But at the level you're at right now, probably isn't that important to know whether this got traced out, whether that entire thing. No, it does tell you data goes from 0 to 2 pi, but I still can't tell whether it got traced out twice. Might have gotten traced out twice going from 0 to 2 pi, which means it would have gotten traced out exactly once going 0 to pi. Although this one looks like it got traced out once going from 0 to 2 pi. That's what it appears to me. Anything else, Demetrius? I don't know what else to tell you about polar.
Yeah, I don't have anything else.
Okay. Well, why don't we call it a session? And yeah, depending, are you going to vectors next?
Yes.
I guess I think I'm okay with vectors. So, although I guess I would ask if you can, if vectors is the next topic, take a picture of the review questions and send them to me before our session.
Okay.
Just because vectors are not my strongest suit, but if I have a little bit of time to look at the problems, I can do a better job of tutoring you on them.
Okay.
Okay.
All right.
So other than that, Demetrius, have a good day, and I'll talk to you next time.
Who's this?
Sounds good. Thank you. You too.
Who made this?
Bye-bye.
Mom?
Bye.